Hello, everyone, and welcome. It is Wednesday, May 13th, and we have a Knowledge Bolide Hangout for the ages. This is a project that Sue, myself, and Mike have been working on for months. It is something that I am super happy and excited to bring you guys. But first, today is our 260th consecutive weekly hangout. The crew is strong, the crew is wise, and we don't miss. So without further introduction, the title, the subject, slag happens. And slag happens everywhere, a lot more than you think, actually. This was a learning process, doing this, putting all this information together for you guys. It's been a learning process, and we did it because most times people approach anyone with something that they think is a meteorite, but it's not. It's either a terrestrial rock or it's what we call slag. So there are so many misidentified pieces of meteorites out there that are really slag. And I'm putting slag in quotations because we'll get to that later on in the presentation. I wanted to ask you guys, why do you think slag could be or is often confused for meteorites? Well, I thought about it, and I think if you think about the formation of them, superheated weird metals, silicas, additives, flux, whatever, planetesimal goo as well, and you get it red hot, you impact it, you pour it out, you cool it in different ways, different speeds, you're gonna get some weird looking stuff. And because the process of meteorite creation and slag or industrial waste creation both require a lot of the same things, they end up looking similar at times. One other thing that stood out in my mind about the creation of these things is the only real difference that comes to mind, besides the ingredients that go into it, is the environment, the atmosphere that it's created in. Some are created here on Earth with gravity and moisture and water. Others are created in space and have a space age. So in the vacuum of space, the cold temperatures and airless void. So it's going to produce different looking things. We didn't learn all of this information on our own about slag and industrial waste and meteorites and how to tell them apart. One of our most popular and successful videos on our channel was directly inspired by the same scientist who we are paying homage to again tonight, with his work on slag and his humor and just who he is. So Sue, could you tell us who inspired a lot of the pictures, the verbiage, the information? A lot of the information online comes directly from one source, and who is that?
Topher, that would be Dr. Randy Korotev.
Yeah.
We love him. I think everyone on the crew has learned a lot from Dr. Korotev. There's so much information, especially on his website. We also used other websites like MindDat, ResearchGate, just a myriad of websites. We're not bringing any new information about slag to everybody, but we're hopefully presenting it in a way that we're focused on telling the difference between slag and meteorites and giving it to you in a video format if you don't want to read or search through the pictures yourself. So we relied really heavily on the Washington University at St. Louis website. A lot of the overwhelming majority of meteorons that we see that have been sent to us, either on, through media or through our white glove program, a lot of them are slag. So that's one of the inspirations of why motivators, I guess, of why we wanted to create this education. I think that Dr. Randy Korotev has the best sense of humor. He has all these flow charts and statistics and maps, pie charts, all these helpful photos, but this was my very favorite flow chart he had on his website. It's so simple. I think it really demonstrates a little bit of his hilarious, sassy sense of humor. Some of these are the responses that Randy would send out. And it was hilarious reading these out loud to Topher because Topher has literally received a version of all of these. And Topher's favorite, if you guys know his personality, is you do not need my opinion if you're already so sure.
Yeah,
So,
love it.
it just like it made me laugh. I just really enjoyed it. And I wanted to share one more example of his sense of humor. Um, and I just loved the lengths that he was willing to go to achieve. I mean, I'm sorry, this is kind of a level of petty, collecting all of the various misspellings of meteorite that made me laugh and like almost fall out of my chair. I just really, I felt a kindred spirit with him. I think it's hilarious. And I imagine that the list is even longer than what's shown here.
Yeah,
So,
really is.
anyways, I just wanted to share a little bit of Randy if you're not familiar with him.
All right. Thank you so much. I appreciate that, Sue. And you worked so hard on this project, so can't wait to show this off. And really, the person that's going to show it off for us is the maestro of the 101, Mr. Mike Kelly himself. That's right. A limited engagement. We have him here all night. Now, Mike Kelly, if you don't know, has been a member of our Knowledge Bolide crew since the very beginning, I want to say. He has been to so many of the meteorite mansions. He is so involved in the meteorite world as far as doing thin sections and just doing so much stuff and hunting them as well. So that's what Mike brings to the table. He has training in geology, but we're going to be talking about some weird stuff today that doesn't come directly from the ground, and that's slag. So maybe Mike, you can explain to us a little bit clearer so we understand exactly what is slag.
Sure, Topher. Thanks and appreciate it. So yeah, got a background in geology, but also did several years of metallurgical stuff, including castings and things like that. So background from experience. So again, slag is going to be a product generated by man, and it's created using high temperatures in order to melt metals. So what you're seeing over here in this picture is a big modified kind of front end loader. And what they're doing is they took the slag off of like a ladle type furnace, ladled it off, and now they are dumping it out into the slag cooling pit. Slag, again, it's mostly metal oxides and silicon dioxide minerals that have formed from the process of all the material you want to remove out of the metal you're trying to get. And so you often get this bubbly appearance, porous appearance to it, a lot of times with a glassy surface. And that's because as you're pulling all these unwanted materials out, you're also creating a lot of unwanted gases with the process, like carbon dioxide, carbon monoxide. And so if those bubbles get trapped, you get porous slag.
Thank you. Just to also be a little bit more clear, this is something that I learned during this research. Slag is not a description of one thing. It is an overarching catch-all because realistically, slag only comes from smelting. But as you're going to get into, there's so many other productions and procedures and refinements that cause industrial waste. So just we're going to point it out several times today, but for today's lesson, slag is an overarching term for industrial waste due to manufacturing of metal and refinement of metal and smelting and things like that. Would you agree, Mike?
Yeah, certainly. And I mean, we talk about a couple other things in this presentation that are adjacent slag, like clinkers. Again, clinker is a very universal term for industrial waste. So one of the things that makes slag a great media wrong is the fact that the surfaces and skins that form on slag oftentimes have a smooth and glassy appearance because they rapidly quench, right? They cool as the slag is poured out or flows out of the production facility. And so you'll get this microcrystalline glassiness to them. And again, to the untrained eye, that's fusion crust.
Yeah. Yeah. We tell people to look for the black or shiny brown black fusion crust flat on the outside of a weird looking rock. That's what we just got described right there, man.
As Topher mentioned, slag comes from, a couple different processes for our overarching term of considering all this different stuff slag. So going from left to right, we got produces the most slag to produces the least slag, right? So smelting is taking unrefined ore, right? The minerals with the metal you want in it right out of the ground and doing a first processing to get it to an intermediate product, a better product, right? And that gets you to refining, right? Refining is taking that first stage metal and then getting it to a purity that you actually want as your finished product, right? So again, if I go from ore to first product, I'm going to produce a lot of waste. If I go from partially refined to highly refined, I'm going to produce a little less waste. Then if I take that metal and I want to change the shape of it, right, that's casting, right? You'll still get a little waste off of it in the processing, but again, much less than refining or smelting. And then finally, welding is taking two really high pure metals and melting the edges together in order to create a joint. And so again, you don't get very much slag off of that process, but there are fluxes involved. So they do produce small amounts of slag.
Thank you, Mike. That was well explained and very important information to keep in mind for the rest of the presentation, because the official slag only comes from the first process, which is taking the ore out of the ground and refining it in the first stage. That is the liquid slag that is by default defined as slag. Everything else in the refining, casting, welding, and metallurgy processes are going to be industrial waste. This is a little animation I thought was really cool here that talks about a blast furnace, and then it cools the stuff down. A scooper comes, picks it up, and brings it to a dump truck. This is how slag gets everywhere. We're going to get into all the details of how it's used, how the different forms of industrial waste and slag are used. But I thought this was a really good animation to show you that it's literally just taken, scooped, moved to a construction site with a dump loader. And we'll be showing you other slides in the future about that. There's so many web pages out there of people who are selling slag. They are selling their industrial waste for different processes, different purposes. So you can actually see a flow chart here, and the tan line in the middle basically shows you where their refined waste is going to go to. Either use in concrete for building, road construction and infrastructure and bridges, metal recovery, and then agricultural and soil conditioning. And Mike's going to talk about that, like shorelines and stuff like that. But just know that there's a lot of processes that create a lot of different types of waste that get used in all types of places unrelated to your rock or where it was found. This is transported there. Mike, one of the reasons why slag is everywhere, and this is kind of something I want to continue to hit on through the entire presentation, is it's not new. Humans have been working with metal, or trying to, for years. Can you give us a brief history? Go as detailed as you want.
Yeah, so you're right. Slag has been around for a really long time. It goes all the way back to the cradle of civilization. So for as long as we've been civilizing, we've been working on metals. So again, Mesopotamia, right? That's the cradle of civilization. That's the Fertile Crescent in the Middle East area, right? You're talking between the Tigris River and the Euphrates River. You're talking where Iraq, Iran, Turkey kind of sits now. And they were originally smelting copper, right? So open bowl type furnaces, just a clay bowl, a leather bellows to blow air onto the coals to get the heat, and copper melts at relatively low temperatures. So it was one of the first metals worked, like 3000 BC and prior. Same thing with the Egyptians. Again, lots of copper. They also, between the Mesopotamia and ancient Egyptian time frame, they figured out you could mix tin in. So if you add tin to copper, you get bronze, right? So it's a slightly tougher metal, and they worked on that for a long time. Then the Romans came along and they started getting the high enough temperatures that you were doing iron, right? So that's the Iron Age. Move on to medieval times, post-Roman era, and basically still producing iron, just producing a heck of a lot more of it. and then move on to the early American colonies, and you're starting to get it produced all over the world in bulk.
Wow, that was amazing. That was a couple thousand years in a couple seconds.
Yep.
Nice. So how much is there?
There's literally millions and millions of tons of this produced every year. And it's a very stable substance. So the stuff that's produced this year is around for 100 years or 1,000 years. So it doesn't go away, and so it just accumulates more and more and more.
Yeah.
We're big into iron and steel because they're construction materials. Major construction materials. So we produce a lot more of that than we do the non-ferrous slags like copper and nickel and zinc. Again, those have their purposes, but we're just not producing as much of them. So you're getting less slag from those processes each year.
Can you reiterate or double point? It's on the screen here. They're separating ferrous or non-ferrous and iron and steel. Can you just punch that home for us, please?
Yeah, sure. So iron and steel typically produce a magnetic slag, right? You're producing magnetic or metals out of there, right? So those are your ferrous metals. And non-ferrous slags are going to be your materials that won't be attracted to a magnet, right? Non-ferrous. And again, one of the interesting things is some of the slags kind of cross over. So non-ferrous slags, if there's some iron oxide in the ore, then they want to drive it out because you're going after copper, right? Your iron oxides are going to end up in the slag. So it's not 100% that the non-ferrous slags are always non-magnetic, but for the most part, they are.
Yeah. Awesome. Thank you, man. I appreciate that. Aren't there meteorites everywhere, though?
Yes, there are. So, so this slide kind of highlights, you're getting between 6,000 to 7,000 specimens added to the ground that are found every year, right? Modern times. That seems like a lot, but when you compare the weight of some of those meteorites, which are a couple of grams, and then you compare it to the millions upon millions of tons of slag produced, you end up with a lot more slag available to be found than meteorites. Also, the meteorites have a relatively even distribution worldwide when they fall. The slag is produced and distributed by people, so it's more in populated areas. And most meteorite hunting is not going to the ends of the earth to find a meteorite. So your probability of finding a piece of slag is higher based on its non-even distribution. Even though it's widely distributed, it's still more popular distributions around where populated areas are.
You were mentioning that meteorites have a even distribution all over the earth, but slag and industrial waste is sort of the same, but it's around manufacturing hotspots, and those are tied to geological places where the resources are rich.
So definitely by some of the European places, when the European slag boom was kind of happening, they figured out early on, let's go ahead and reuse this material. So it's actually incorporated into like castle walls and things. So it's been an important reusable material from the early Iron Age. Other things like in northern France, they've actually turned a couple of their very large slag piles into World Heritage sites to kind of highlight the important industrial processes that were going on there. And you're talking about slag heaps that are on the order of 246 meters tall.
Wow.
Right. So these are basically small mountains of slag to give you an idea of how much they were ramping up production. Same thing. We highlight Asia because like China is like the number one slag producer in the world right now because they're the number one steel producer. So again, make a lot of steel, make a lot of slag, and have a lot of material you have to deal with. So there are literal mountains of slag over there. Getting a little closer to home, Pennsylvania was a major steel producer for the United States. It was Bethlehem Steel was the second largest producer of iron and steel in the country. And so that's a very famous steel site. They made steel that was involved with building the Empire State Building, the Golden Gate Bridge, battleships. They built over 1,000 warships during World War II with the steel out of that plant. It's not just Pennsylvania, though. Arizona and Florida
That's
all had areas that have been major industrial areas for refinement of metals. Same thing, Scandinavia, you're talking over by like Sweden and Norway. They've been major producers for Europe. And you can't negate places like South Africa that are very old and very early on producers of iron. And so there's historically important sites there where they're doing research to figure out, how accurate and what processes did they use to make these metals early on. And so, yeah, it's a very interesting way to look at history.
It's just to show everyone how interesting this kind of stuff can be. Uh, the Arizona one, those are mainly copper, and there's a lot of copper mining in Arizona, but that's where I am. Mike is over in Pennsylvania, and he is dealing with the Bethlehem Steel Company. You actually visited them with your family.
Yes, certainly. Yeah, I went there. So they stopped producing in the 1990s, and the company was disincorporated in the early 2000s. But the site has been preserved, and they spent $15 million. So what you're
Wow.
looking at here is the Hoover Mason elevated rail track, and basically what they did is in the background, you see the actual blast furnaces, and there were 5 of them up there. And those blast furnaces were capable of producing up to 3,000 tons of steel each per day, iron per day. And that big metal structure in the front is an elevated causeway that the rail cars pulled up on to deposit coal and deposit limestone and deposit iron ore that fed those furnaces. Yeah, so this is just some inside views of like the big power generation aspects to the plant that are still preserved that you can go and see and just tour anytime between like 8 in the morning to 8 at night at the location.
I learned during this research that once a blast furnace is started, they don't stop it.
Correct. Yeah, they can run until they need maintenance, and so they're costly to build. They're cheap to continuously run, and so they just keep running them as long as they can. And you add materials in the top. You blast in highly oxygenated hot air in the bottom, thus the name blast furnace. And basically, the ores melt, and the product rains down the inside of the big chimney and comes out the bottom as pig iron, and then the slag comes out mid chimney off the top as slag.
Beautiful family, by the way. Thanks for including this picture, man.
Yeah, so yeah, this is one of the events they do over at the Steel Stacks every year, which is Peep Fest. So that was my reason for being there.
Nice. Yeah, this is China we're looking at now.
The technology has come a decently long way. The principles are still the same, but they scale it up. And like you said, these are running 24/7. And if you have to shut it down once every couple of years to clean it out, that's all you do.
Yeah. And if you look at the infrastructure built just to support those stacks and the furnaces, there is massive material movement orchestration going on behind the scenes. Railroad tracks and conveyors and all kinds of stuff moving massive amounts of weight because we're talking about the amount of slag they produce. That's the garbage. They're worried about the irons, the steels, all the crap that's not slag. We talked a little bit about different methods and procedures that create slag, and here are some of them. This is one company in India. This is what they sell. This is what they do. They buy industrial waste from all these processes and then sell it. So what you're actually looking at here is not a dump. You're looking at their inventory. It's ubiquitous. It's everywhere around the world, and different countries deal with it different ways. Mike, did you have any comment on this one?
Yeah, just like you said, like that initial flow chart showed, it can come out of the production of iron and steel and other metals and automatically become waste, but it can also be highly useful if reused, and that gets a second life out of the material. And one of the things that's important about that is it displaces other things you would mine rock for. So why am I going to do environmental damage to mine more stone to be the construction material when I have a material already ready made and already closer to where I'm manufacturing things, since it's kind of in, urban environments, industrial environments, that I can reuse. Why is slag found in so many random places? That's part of what we kind of just discussed, right? So the slag doesn't stay isolated by the foundry or the refinery where it's made. It goes ahead and it gets used for all these secondary processes, and that spreads it out to everywhere you're going to possibly ever walk in your life. And this shows railroad ballast. And again, instead of mining stone and putting it down, railroad tracks need to be very stable. So the rocks need to interlock. Slag breaks into jagged chunks, and those interlock very well. So it makes great railroad ballast. Find something, and they'll associate slag with railroad ballast, and they'll say, well, I was nowhere near a railroad track. Well, they come and they go, and they get repaired every several years, and they pull the ties out and they pull that underlayment out, and then they redistribute it even further. And back in the day, they didn't send it to a nice dump to be processed. They just hauled it off somewhere and dumped it into a location they didn't care about. Not too far away, but far enough away that it was out of the way. Yep. And so it's a constantly moving process. Just because there's no railroad track there or you're a couple miles away doesn't mean it didn't come from a railroad source. Slag is also very useful for both elements of concrete. So concrete's a combination of aggregate and also cement. To a degree, slags, if they're processed correctly, can be decent cementing agents. And the image you showed where they were initially pumping slag out of a pipe and then you saw some sprinkler heads kind of cooling it. Part of that process and why you would cool it is so you can change the material properties and make it a good either aggregate or a good binder, so a cement. And both of those things are come together for a concrete.
And then that concrete goes all around the world and built in buildings that don't last forever. And then they get broken down and that slag gets distributed even further.
Exactly. Yep. So road construction is very similar to railroad construction, right? You want a very good, stable underlayment to your road surface. So again, you're going to use the slag as an aggregate, and you're going to process it and crush it up, get it nice and angular, get it to bite in there, so you get good compaction and it stays stable for a really long time without having to need to be recompacted.
I think it's really, really key that you pointed out something there, because a lot of times when we see pieces of slag, we're looking at hand samples, big ones, and we're flipping it over and rotating it. The slag that we're talking about in construction, road construction and cement construction, you were pointing out very well that it's pulverized, it's crushed, it's not used. You're not going to find bricks of slag. It's been refined for these processes.
Yes, and Topher, actually for roads, they'll do things like a sub bed and then a bed, right? So the sub bed will be coarser, so they'll prep the material less, so it's a coarser aggregate, and then as they lay further layers on top, they get finer and finer until they get to their proper grade. So it's not just one material fits all as far as prepping your slag.
Yeah, if you want to go down a rabbit hole, you can look online and try to buy slag, because like you were saying, with the spraying of the water, they were cooling it down at a certain rate, blowing air through it, pouring it on the ground. All these things are going to change what it looks like, how it comes out. If it's going to be a sheet or if it's going to be aerated and bubbly and porous and things like that.
Yeah, so shoreline reconstruction is not that much different. Again, you're going to have much coarser aggregates here. You're not going to break up that slag as much because, again, you're fighting Mother Nature. You want that coarse locked material to be very large, maybe even boulder size, right? So they can use bigger quantities and do less processing. And again, you might take that fine slag and use it for your roads, and your medium slag and use it for your railroads, and use your very coarse slag for things like shoreline stabilization projects, where you're trying to stop the ocean from moving around all that other material around it.
Wow.
Yeah, so harbors are similar to shorelines. Again, they're usually calmer waters, but you want necessarily a bottom that might not move around in a harbor. So you might want to put a layment of slag down in order to create a stable base that's going to stay flat and not grow things and prevent silting. So again, slag is really useful for areas that are even more calm watered.
Porous, very porous slag or industrial waste is also used for uh, encouraging coral growth in coral areas. I don't know if you knew about
Yes.
that.
Yeah, it's used for that. It's also used in sanitation of liquid wastes for the same reason. Those pore spaces are used to harbor good bacteria that kill the bad bacteria.
What's in slag?
There's a lot of things in slag, but the majority of it is iron and other metal oxides. So that might be iron, aluminum, magnesium, or phosphorus. And then you have things like calcium. So again, when they're making things like pig iron, they're going to put limestone in there. The limestone is going to break down CaCO3. You're going to get CaO, calcium oxide. And basically, what that's designed to do is bond with all the impurities in that liquid metal and draw them up to the top. So you'll get calcium silicates that float up along with some iron that comes out of the system. It's not a perfect system, and then all the other type of metals you want to drive out.
Yeah. And there's a lot of different processes that I didn't even understand. I couldn't even get into because the rabbit hole was deep. But maybe you can. Are you familiar with BOF and EF, BOF and EAF, and how are
Yeah,
they different?
so one's a basic oxygen furnace and one's an electric arc furnace. So that's what those two acronyms are for. And those are actually for producing steel. So you use a blast furnace to make the iron. You blast in that super hot air at the bottom, and you actually are reducing the metal to drive the oxides out, right? Because it's iron oxide you're using as your ore. Then you want to turn it into steel. So there's iron and about 4 to 6% carbon left in that pig iron, and you now need to drive that carbon out. So if you're using virgin material, right, virgin pig iron, you're going to use a BOF, right? And basically what that is it's like a ladle type furnace. So it's not continuously run; they run it in batches. It's got a chilled pipe that blasts oxygen in. Now you'd be like, hey, I'm oxidizing things. I just deoxidized it in
Mm-hmm.
the other furnace. Well, the carbon preferentially oxidizes more than the iron does. So yeah, they produce a little iron oxide. There's more slag, right? But you oxidize all that carbon out. And then you end up with a product that's basically steel at that point. You've gotten that carbon down to a fraction of a percentage. Um, and you have now low carbon steel. Electric arc furnaces, those are used for working with scrap metal. So if I start with different scrap iron and scrap steel and I want to reheat it and reprocess it into another form of steel, I use that electric arc furnace.
Wow. See, there's so many different starting ingredients, processes, a myriad of them. I actually learned a little bit about foundry and casting. So correct me if I go awry here, but foundries don't produce slag, they produce foundry waste. And that is basically because they're pouring that liquid metal, they've already refined the metal basically, and they're pouring it into a mold. They're in a foundry or a casting. They're pouring it into a mold either of salt, of sand, or some other substrate that could contaminate the metal. Um, and that's why we see some pieces when we see someone say, "Oh, that's slag. It's not a meteorite, it's slag." And you look at it, and it has sand. It's all sandy. And like, how could it be sandy yet be slag? And it's from the foundry, the casting materials around the molding process.
Yeah, no, you're basically right. And again, same thing. When they're casting and they're pouring the metal in there, there's little bits of flux and other things. So yeah, it's more secondary materials, like you're saying, like industrial waste. They could do things like lost wax casting, right, where the original item is made out of wax inside the mold, and then the hot metal displaces the wax because it's higher
Oh,
density, and kind of burns it out, but you get all sorts of gunk left from that wax and the release agents that so it doesn't stick to the sides of the cast. So yeah, you're absolutely right.
If you're a rock counter and you have a sample that is 70, even 90% sand, silicates, and we're calling it slag, it's foundry industrial waste, casting industrial waste.
So we touched on this a little earlier. Again, those ferrous slags, a lot of times they can't, trap 100% of the iron or steel that they're looking to make. So they'll end up being magnetic in nature, and the non-ferrous ones obviously won't unless there was kind of iron contamination to begin with in the ores. But again, this is just another great image of, a massive place that, they filled up these crucibles on rail cars that then the train drives over to a big slag pit and they just pour that material out. And that can be a really dangerous operation, right? If you ever want to see crazy videos, if they're pouring it onto ground that it's too moist, and the slag can't get out of the way quick enough to let all that steam get out of the way, you'll get what's called a slag explosion.
I watched
And
the video.
Yeah.
Yeah, I don't want to be anywhere in the same town when something like that happens. Yeah, imagine that's not a 55-gallon drum. That's 500 gallons, whatever, and it literally went off like a bomb.
Yeah. Yep. Yeah. Though that rapid expansion of steam can be very deadly to the people who are actually doing these processes. It's not a very risky business.
This place right here, this is massive. Like that is huge, and you can see the way the slag is cooked and caked on the walls, and then down at the bottom of the pit, you can see it's flowed differently. It's cooled and tumbled a little bit, maybe got a little bit of outside edges. So yeah, I think it's really telling when you see something like this. There's another word, euphemism, colloquialism that we hear a lot. I ran into a lot while doing this presentation, and that's coal clinker. It's not really. Is it industrial waste? It's not slag. It's the silicates that were in the coal vein. Correct?
Yes. So clinker is kind of a universal term for waste. So a clinker slag can be clinkers. Clinkers can kind of be considered slag. There's a kind of a gray area there. But yeah, you're absolutely right. So the most common clinker that is a meteor wrong is coal clinkers. And so if you want to make a really good burning fuel, you take coal and you put it in a oxygen-free environment when you burn it, and you create coke. Now, the coke melts and forms a solid product towards the bottom, but then there's all this other stuff that melts that's not carbon-based. That's like you said, your silicates, some of the ash from burning it off melts and gets recrystallized. And so all that other stuff that's not the coke is the clinker.
Okay, nice. Thank you, man.
Kind of an interesting side fact on that one when you were talking, just to loop back to slag in the wild. Yeah. So coal clinkers end up in a lot of places you wouldn't think you would find them because of old steamships. The steamships actually burn the coal, and every once in a while in their furnaces, they produced clinkers, and they had to clean out the furnaces on the ships, and they just dumped it overboard. So along all those shipping routes, you find coal clinkers at the bottom of rivers and oceans and bays from all that the old age of steam engines.
Man, we've already kind of talked about this a little bit because it's industrial waste. But if you can engineer the industrial waste to have some value when you're done with it to pass on to someone else, that's what this slide is talking to. It talks about different ways of cooling them, whether it's ambient temperatures like we just saw in your example of them dumping the rail cars out. Earlier, we saw the air quenching and water spray. That's another way. And then we didn't show this one, but jets of water and stuff. And it all affects the cooling rate. And we're bringing this all around to meteorites because we talked about the weird compilation of ingredients, high temperatures, different cooling rates, and how they're similar to meteorites. So let's take a look at some of these and we're going to take a look at meteorites as well. So I think that's why a lot of people are comparing these two or getting them confused, because you don't just walk out, even though there's slag everywhere. You just don't walk up and pick up a piece normally. You know what I mean? So when you find something like that, it sticks out and like, wow, what is this? And no one wants to hear that their precious rock, their beautiful thing they found, is waste, is slag, is something that no one wants. So here are some other, I'll let you talk about this. These are some other methods or finished slag product. This is not the slag as it came out during the production, correct?
Yes, yes. Like you said, so you're using one of those treatments you just mentioned in the previous slide in order to get a better end product. So granulated is exactly what it sounds like. I want the slag to be tiny little pieces, broken up, and I want it to be almost more of a smooth texture. So vitrified means glassy. And so if you quench the material, right, you get it to cool very fast. It doesn't have time to form bigger crystals inside the material, and you'll get a glassy, very fine grained slag like what you see here. Iron furnace slag. Again, this is probably very old type slag. Old school iron furnaces were called bloom furnaces, and they were basically like a little straw and clay chimney. These are your really ancient ones that were just spread out all over the place, and they literally just broke it down when they were done and pulled out a chunk of metal from the bottom that was, maybe 80% iron, if they were lucky, and then they refined it more. So you would get these chunks from the blooms, and they would have coarser other things mixed in there from the limestone they were pouring in there. And so you'll get these bigger, weird chunks.
Yeah, and these get mistaken for iron meteorites quite often.
Yes. Again, that iron furnace slag, it can get vesicular. Again, when you're making iron, you're producing a lot of carbon dioxide, so it's trying to escape and get up out of the slag. And if it doesn't make it out before it solidifies, that's what you're looking at right there.
And if you look at the shape of the bubbles, the vesicles, that's also a diagnostic tool for us to tell slag from meteorites. We usually don't see the stretched out, weird shaped vesicles that we're seeing here. They're normally in meteorites more likely perfect spheres around domes.
Yes, exactly.
People get insulted when we say it's slag, but we're going to take a look at some pictures of slag that's actually really interesting looking. Like, if this was a meteorite and if it was justified by science, I would have that in my collection. That's unique looking right there. But that's copper slag. This is one that we see a lot of. Do you have any idea or any information to add to this? Because this is a very, very commonly mistaken for a meteorite.
Yeah, so this is another copper slag, and it's probably decently oxidized. You're not getting a lot of the greens, and sometimes you'll get that with the coppers. But again, it's smaller production, batches usually when they're doing copper, so they're not having these huge pours. So it's not surprising you're seeing this little rounded bit off of there that kind of looks like an oriented meteorite, right?
Yeah. We're putting all these pictures in here not to overwhelm and see how many different things can I get Mike to say, but to show everyone that there's so many different varieties of industrial waste, furnace slag, smelting slag. There's a plethora of it out there. All right, Mike, maybe you can help do a little bit more educating for the slower ones like me about coal clinkers. This was listed as a coal clinker. What I'm seeing in this picture is a bunch of black, like especially on the right-hand side. I think that looks like coal. The material in that's not coal, in this big rock in the center, is that what's going to, this rock is going to be thrown into a heating process. The silicate's going to be melted out, and that's going to make the coal clinker. Am I correct?
Yes, yeah. So the coal goes into a furnace to turn it into coke. They basically take out the oxygen as they're adding in the heat, and then the coal basically turns into a pure form of carbon, and all of the impurities get moved out. So yeah, you're seeing mostly melted silicates in that big tan chunks. And then obviously it's not a perfect process. So, that those little black veins binding through there are probably little bits of coke that still got mixed in there.
Let me interject for 1 second. I've learned, this is not out of the ground. This is the coal clinker. This is after the fire, after the heat. This is the waste product, one in the center.
Yes. The interesting thing about coal clinkers are sometimes coal veins catch on fire out in nature, and they can actually form coal clinkers naturally.
Yeah.
So
Yeah.
I don't know if this is a picture from cleaning out a furnace or a picture of potentially like a mine fire area where they're trying to get in there and stop it from burning underground.
I'm glad you pointed out, because this is a USGS picture, and they listed it as naturally occurring coal clinker. So you're
Yes.
dead on, dude. Dead on. Thank you. We have other ones. This is like this right here. I don't know if this is safe or not, but it looks like lava rocks that you use in your landscaping.
Yeah, and so dry pit slag, basically we were talking about, you can put moisture on there to cause it to break up or granulate faster, but for stuff like you said, if you wanted to use things kind of in landscaping, I don't think I would use barbecue pit. It might not be good for your hamburger.
Yeah.
But you're going to want a little coarser material, and you don't really care what the surface treatment is, and so the stuff on the top of the pit is going to quench and cool faster, but you're going to trap a lot of gas in there. It's going to be porous.
Yeah.
The bottom stuff has longer time to cool down, so it's going to cause bigger crystals to grow inside of there, and it's going to be a coarser material.
This is an example of foundry waste. Again, you can see in the very center of like some very unmeteoritic features, things that really stand out to us immediately. But this just shows that they can be, like Mike said earlier, they can be massive chunks. They could be big things used for shoring up harbor lines and stuff like that. I saw some examples of monsters, like 50-kilo chunks of it just laying around. These are hand-sized bricks, but it comes in all shapes and can be broken down for any application as well. I wanted to include this one because I didn't want anyone to ever give me a hard time about not paying homage to terrestrial items. This is a terrestrial item, but it has a museum number. This is a 1889 copper slag from Wales. And you did mention earlier that the UK was one of the hotbeds of metallurgy working. So this is in the museum somewhere. So slag is important enough to make it in museums and get hand numbered. So this is another one that I didn't find this at a science or manufacturing webpage. This is from Heinrich Minerals. This is from a very an art gallery. So this is copper slag that is now being sold as, I don't want to say expensive, but it's being sold as art. Mike, do you have anything to say on these at all?
No, I'm guessing that's probably a very old slag, which probably adds some value to it because it's got a lot of copper still in it, right? So it's probably a poorly done refining process because you're getting a lot of the copper you wanted to save in the loss. But again, it's interesting the way it flows and it gets that patina and that green copper look to it. So I can see it as art.
This is one thing that I kind of had a hard time wrapping my head around, the glass of it, the glassiness of it, because everything I'm seeing, everything I'm thinking about in my small brain that we've been talking about, all should be metallic or silicas. But I really don't think those silicas are going to turn into glass, are they? Look at these things.
If you cool that material quick enough and give it no time to form crystals at all, right, you form glass, right? So compositionally, it's a silicate, but that's the same way to say as the same as saying, sand is refined and then pure silica can be melted down and turned into glass if it's quenched. So yeah, you produce glasses like that at the very top of the slag uh, pool sometimes when they cool it quick enough.
These are here from the 1870s, so these have been kept and held around for a while in someone's collection. If you look at that green one on the bottom there, we have a picture coming up later on, a close-up of it. It looks like trinitite. It looks really like it was caused under that much pressure and heat.
You
I
kind of touched on this earlier, Topher, that people kind of get insulted when we say, "Well, it's not a meteorite; it's slag," but it's really interesting, and sometimes we get that response. Yeah, okay, but it's true. There's a lot of really interesting slag, and I collected these because I thought these were all pretty, and I have a terrestrial like mineral collection. I would love to have these. The one on the right hand side is copper. The two in the middle are considered glass slag, but the one on the left I thought was the most interesting. It actually has a name. It's called Marienstein. I think that's how you pronounce it. Maybe Marienstein slag. It's from a very specific area of Germany, and it's turquoise colored. Obviously, it's water worn iron slag, and so it's not natural. It's totally man made. But people find it like in rivers and streams now, just because it's historic. It was made a long time ago, but I just thought it's actually really beautiful.
Before this research, I never would have put these on slag. Maybe the one on the right a little bit. It's airy and populous in the back and has a little bit, but that one in the top center looks like obsidian. It looks like obsidian glass to me, you know? Now that we know what slag is, what's in it, where it comes from, how it's made, how it's distributed all over the world, and why it's confused with meteorites. Now we got to take off our glasses and clean our eyeballs off a little bit. Use a little Windex if you have to. We're going to be looking at some meteorites now, and hopefully we'll be showing you a little bit of side-by-side comparison. You've been absconsed in industrial waste for the last little bit, so now we're going to talk about actual extraterrestrial material.
The exterior of slags, oftentimes, since it's poured, it'll have rounded and relatively smooth features. Again, you pour it, and it's basically liquid silicates with little bits of iron and other metals in it. It's going to flow as it moves downhill, right? Because they're usually dumping these into big pits. And so you're going to get flow patterns, very coarse, thick, ropey flow patterns on the exterior surfaces there. And a lot of people confuse that for flow lines. But like I said, when you get to the meteorites, you'll see the difference in magnitude.
This one shows those hard flow that you were talking about, deep in the rock, if you will.
Mm-hmm.
Whereas that, I will tell you, is a meteorite. It is a beautiful meteorite. I think it's named Bruno, if I remember correctly. It's a single stone iron that fell in Canada. And any chance I get to show this off, I do. It's not mine, but any chance I get to show this off, I do. But it shows you the surface features of absolutely 100% perfect flow lines in iron. You're never going to find one that looks like this. This is the touchstone that you should be comparing your found examples to.
So slag, it's usually dark in color. Again, you're creating a lot of iron oxides. So you're going to get your dark blacks, you're going to get your dark browns. But there are potential that you have other oxidized metals in there that kind of give a peacockish patina to it. So you can see very odd colors on the outside of slags that are metallic and shiny and purplish or greenish sheening or to bluish sheen, which some meteorites form metal vapors as they're coming through the crust and get a similar appearance.
Yeah, Mike, this is a great example of what you were just talking about the iridescent crust on a meteorite. Obviously, the one on the right is Aquazarchus, and it's probably one of the best examples I've ever seen of iridescent crust. Whereas on the other side, the slag, kind of not the best example, but you can see the iridescence of it. But it looks, the texture of it looks totally night and day different. More external features explained in a way comparing, contrasting to meteorites is we look at the outside divots, regmaglyphs, whatever.
Slag is forming bubbles in there, and those bubbles are popping. So the mechanism of formation is different, and it leads to kind of sharp shoulders or sharp edges on those popped vesicles, or cut into vesicles if they solidified inside and you break it open. And a lot of people mix those up for regmaglyphs, but regmaglyphs are like thumbprints. Imagine they're often explained as pushing your finger into soft clay. So when you do that, the material deforms plastically and it forms a rounded, soft shoulder. So there are no hard edges to those. And that's something to look for to try to tell a slag from a meteorite.
Yeah, very good. And you can actually see on these on the very top how they have hard, well-defined edges. They look sharp. You, if you rubbed your apple against it, it would peel your apple. Okay, meteorites, the regmaglyphs are not going to be like that, as you were saying. They're shallow, they're soft. This is a good slide. Again, Randy Korotev knocking it out of the park, showing those vesicles and air holes. This is the one I alluded to earlier that looks like the atomic glass, the trinitite. Not really, but it's the most, it resembles it the most. But you can see in here little beads of sand. Like, this was confusing to me when I saw liquefied glass with sand in it. Do you have any idea what we could be looking at all, Mike? And I'm putting you on the spot.
It could be foundry waste, like cast copper, where it was warm enough to melt the copper and the sand together, kind of forming a glass. That would be my thought.
But when I saw this, I was like, that's cool. I like that a lot. It totally reminds me of trinitite. This was a great one. Look at that right there. That's a perfect shot to show you that, hey, we talk about anything and everything's possible. We are talking in the most general but realistic, covering 90% logic. There's going to be some weird outliers there, like this weed name is 001. It's an angrite. It's volcanic. It has these vesicles, these round vesicles in it that look extremely similar to what we're seeing here in this piece of slag. So when you look at them side by side, you could look at them and go and say, see, they're identical. Well, no, they're not. They appear to be, but this one on the left has fusion crust, very obvious, and has crystals on the inside. When you look at it under a microscope, it's night and day difference. Notice also how the inside of the bubbles of the slag are shiny and glassy, where that's not true on the meteorite. So that's another way to tell similar looking features apart, even when you put them side by side and you go, see, they're the same. No, they're not. And it takes exposure and knowledge, experience, touching, looking, getting under the microscope with these things, because that's how you dig in and learn, not just by looking at slag and going, that's got to be X, Y, and Z. No, take a piece of X, Y, and Z, look at them side by side. How similar do they look now? If I ever get a chance to put this video in, I do. For those that know, this is a huge chunk of the Chelyabinsk meteorite. Wanted to show an example of regmaglyphs. Again, just like Mike said, they're soft indentations, look like finger in soft clay Play-Doh material. If they are elongated, they're all elongated in an aligned manner. They're fluted regmaglyphs. They're all in the same direction, showing the angle of air. They're only on one side because that's the only external side of this meteorite. Everything else was an internal side that got a little bit ablated at the last final part. That is a great example of regmaglyphs, fluted regmaglyphs, just the surface area of a meteorite versus industrial waste.
So moving on to the interior, the breaks inside of slag are typically rough and jagged because of the nature of the material. And again, that's a feature that's actually useful in slag to get it to bond with the pieces next to it, like we discussed when you're using it for things in construction.
Yeah, this is a good time for me to talk about ballasts. I wasn't 100% familiar with the term. I was aware of the term more associated with what Mike was saying here, a railroad ballast, where they put it down, they basically shake it, but compact it. It's angular, it interlocks, it makes a good bed, and they put the railroad tracks on top. But ballast is also a term to describe weight, some kind of heavy material, sand, metal, rocks, water, that vessels will take on, whether it's a hot air balloon with their sandbags, that's their ballast, whether it's shipping and cargo. In the past, all used to be ballast. They have to put their load in there and then balance the boat or the ship with some heavy material in the bottom. But since then, it's not all industrial waste. It's not all slag. SS Topher's treasure is ready to set sail. So before we leave the dock, we need to ballast and balance our boat. And we don't do it with rock and slag anymore. Then the common normalized modernized way is with water. So water ballasts are being used now, but that's actually replacing the old rock ballast and that's good because we're not shipping this industrial waste all over the planet anymore and having shipwrecks. This is another learning experience. If you had no idea, when you see ships dumping water like that, if you had no idea what they were doing, now you do. Oh, Mike, this doesn't really fit into our conversation, but I wanted to bring it up because we bring up magnetism and magnetic response and stuff. Can you explain what lodestone is? Just because we don't understand it, we're lost.
Yeah, sure. So lodestone is a naturally occurring, basically magnetic compass. So if you take a piece of magnetite, something that would be attracted to a magnet, and it's warm enough and exposed to a magnetic field, all the iron particles in it will align, and you'll basically get a naturally occurring magnet. So lodestone literally means guide stone, right? So that was basically an old time natural compass that if you were to float that on something, it's going to act as a compass and align itself with magnetic north.
Wow. So if you obviously apply your rare earth magnet to it, it's going to go right to it.
Yeah.
And it catches a lot of people's attention. It's probably going to set off metal detectors. So people are finding it. But just to clarify, these are these are naturally occurring. They're not industrial waste.
Nope, they are not industrial waste, but if the iron content is good enough, they make good ore for making industrial waste later on.
Ah, nice.
So fill materials, exactly like we were talking about through most of the presentation, is if I can use something that I already have and it's nearby, it's convenient, and for the most part, back in the day, it was free, right? Iron places were trying to get rid of their slag, and if you were willing to go haul it off, they were happy to give it to you. Before they figured out that it's got commercial value and they could sell it to you now.
Yeah.
So yeah, it's great for just a fill material in construction, in using it in gardens, things like that, as a top cover to stop weeds from growing. Again, it's got all sorts of purposes as just bulk space occupier.
And here's another example of what I wouldn't have selected off the shelf as slag. It's white. You know what I mean? You think by the exposure that slag is going to be black, brown, it's going to be metallic. This looks like silicates. It looks like, you know what I mean? So that's one thing I really wanted to point out through this entire conversation was how different and widely things vary. And that's exactly what this is talking about here. You want to talk about zinc and lead?
Yeah. So again, some of these more niche metals that they're getting metal out and producing the slags. A lot of those, like I mentioned before, they'll use salts as the fluxes. So you'll get a high salt content material, and again, that's going to have a vastly different texture and look, like you said, color and composition, than maybe like an iron slag with the darker oxides, high iron oxide contents. Again, you'll get chunks of metal in there that are less refined, and so you can kind of get something that looks kind of more like a mesosiderite, where there's a lot more metal lost to the process because it's less efficient. Because again, we've been doing zinc for a long time. We've been doing lead for a really long time.
We were talking about and showing examples of industrial waste just now that had, to me, it looked like no metals. They looked like the white paving things. Now we're looking at stuff, and if you look at it, you're like, wow, some hunks of metal in there, some nice bits of iron. Like, it looks like a meteorite. It looks like you could pick it out and go, well, that's a mesosita right there. Because you're seeing it separate from. Mike, this is a piece of beautiful slag that you took a picture of. Which one is this?
Yeah, so this is actually a piece of slag that was sent to me from one of my friends, Mikey Boland. So this was something he found. He hunted all the time and found very interesting types of slag out in the wild.
Wow. Is that translucently backlit just there?
No, that's reflector light coming off of there.
Oh, okay. Wow. Okay. Lots of metal in that one.
Yes, lots of metal in there. But very fine kind of crystalline matrix around all that metal, which is
Yeah.
interesting.
This is a real deal. This is a meteorite. This is, I said the other ones looked like they could be mesositerites. This is a real mesosiderite. If you look at the metal distribution and the actual structure of the metal, it's different. It's meteoritic. Look at that big nodule of metal there. There's a metal inside the metal. And in the center of the screen now, there's larger crystals showing a slower cooling and growth rather than what we're talking about here with industrial waste being cooled down. So that's another. These are all little hints and tricks and clues to look for to either prove a meteorite or prove a terrestrial sample.
Like I said, you can see it looks like there's a little grain of troilite inside the metal there, and you'd be hard pressed. You do get some sulfates and the sulfides forming in slag, but not overly often. So yeah, it's a telltale giveaway that that's likely a meteorite.
Ah, the mighty Googe, the Googeba. This is one that I'll be honest with you, it doesn't look like a meteorite. It looks like industrial waste, but it's so gorgeous. But this is one meteorite where we literally see these metal blobs, these metal chondrules, and no real distribution other than that. It's a very, very unique meteorite to have beads of metal in it. And a lot of times there's beads of metal in industrial waste that if you cut it open, look like this. The bencobanite types are the only ones we really see metal chondrules, round metal balls. That's unseen in meteorite. This is an outlier. We want to really drive the point home and show more of Randy's pictures, Dr. Korotev. And Mike, if you want to add anything here, you can. But what I'm seeing here is a bunch of different surface cooling flow features. I'm seeing a lot of vesicles, and especially on the one on the bottom right, I'm seeing just a plethora of silicas and contaminations. And I only see flow lines in one little area, and it's not on the surface. So I'm looking at everything here as being slag. Even the top right one that looks like it's all glass.
Yeah, no, you're right on. The feature size is way too big to be meteoritic flow lines. That's indicative of a slaggy material. It's fine grained, so it had time to flow, but it also cooled relatively quick. For being on top of a big pile of molten waste.
Put this in here because this is what flow lines look like. Yeah, this is the point in time where we when I said earlier, take off your glasses, wipe your eyes, Windex if you have to. Like, we'll get the industrial waste off your screen for a second. These are just an example of some beautiful Sakota lens, a witness Russian iron fall, and you can see the organization, the structure. I almost want to call it the intelligence behind the flow lines. They all originate at the leading tip. They all follow a straight line parallel towards the back, wrapping around sides. Telltale flow lines in iron. I showed you some earlier that were swirling around the regmaglyphs. That's what you're going to get on a surface of an iron meteorite. It's going to have those regmaglyphs that Mike talked about, the soft indentations, and then it's going to have these flow lines in there like we showed you earlier with Bruno. But when it's not a regmaglyph and it is just a piece of metal, it is an oriented meteorite, that is it. It could have those flow lines on both sides, one side or anywhere. But that is exactly what you're looking for as far as flow lines on a meteorite go. They're really small, they're really fine, they're metal, but they're delicate. They're not like the other screen we just saw with big old tubes and whatever. Wow. That is a beautiful camel.
That is.
Oh my gosh. The flow lines are just so fine and shiny. On the bottom side here, it looks like it's all
glass. That's even glassier.
Yeah.
And even, you can see it's even weathered a bit. Can you imagine this was even shinier at one point? I mean, that is just, I mean, look at that flow.
That is crazy.
Look at the flow there.
Wow.
That is
one
of these days I'll drop it.
No, please.
I'll just glue it back together.
Thank you, Lawrence. Here's a cool quote from Mitch Noda, who's a meteorite collector, and he's an IMCA member. He made a comment about I mentioned the Carlton Moore. When ASU received the Carlton Moore collection, it put them on the map as having one of the world's finest collections. My thank yous to Dr. Lawrence Garvey and Busick Center for Meteorites for sharing this with us. This is a camel donga. It's a eucrite, which is known for its glassy fusion crust. And here's a perfect example to show the fusion crust, flow lines, regmaglyph divots. I think this thing speaks for itself. It's absolutely gorgeous. Everything that we're talking about with slag, about the beginning ingredients, the heating processes, the cooling processes, what was done afterward, all affects what they look like. Exactly like meteorites. The composition of the meteorite is going to really, really point to what the fusion crust is going to look like. On that beautiful Cameldonga eucrite we just saw, a real thin, glassy, see-through almost fusion crust. Very delicate, very beautiful, and glassy. If you look at this one here, I believe this is El Hassan Ul Hamed, and it's a witnessed Algerian fall. Well, you can see how thick that fusion crust is, how black that fusion crust is. It has the brown patches in there as well. And it's a clear, distinct color difference from the inside and the outside of the meteorite. So this is contradictory to the top of the screen where it says slag have no clear boundaries. This is a meteorite. It obviously has a super clear boundary. You can see the crust. You can see textures and feel textures of the crust, and then obviously get a good look inside the actual meteorite itself. Oh, yeah, El Hassan Ul Hamed. This is beautiful material. You can see how thick the fusion crust is on it. And guess what? It's only on the outside. This is the inside. When you cut it open, you see obviously a bunch of chondrules, a bunch of well-dispersed nickel, iron, metal, exactly like we'd expect to see in a meteorite. So the texture of the outside of this is very indicative of meteoritic fusion crust. This is just another beautiful example of a meteorite that shows the soft indentations of the wind regmaglyphs, shows the thinness of fusion crust, the relative size of the contraction cracks, and the different color, internal and external. And also, if you look close enough, you can actually see chondrules in the bottom hole. So these are things that we did not see on any of the slag earlier. We might have seen a smooth surface, yes, but nothing else matched up. So as a rock counter, when you're examining your sample, please don't get ultra highly focused on one thing and ignore all the other things. There's like 5 or 6 things in this picture that you can pick out as meteoritic. And you should be able to look at your slag or your sample and be able to pick out different things as well and put them on a list. Is it a industrial waste or is it a feature of a meteorite? And when you're done, you should be able to have a little bit better idea of what you have. There's no mistaking a meteorite if it has a Wittgenstein pattern on the inside. When you cut it open and it etches, and you etch it with acid, you're going to see a predictable pattern, a logical pattern. That pattern, the Wittgenstein pattern, is the metals pushing against and separating from each other over a very, very, very eons long cooling process. Hundreds of thousands, millions of years of cooling versus a day of them dumping out the slag and it cooling really quickly. So these crystals, this Wittgenstein pattern, cannot happen in man-made material that is just poured out and quenched. These take time to grow. One is a meteorite, one is not. If you look at the meteorite one, the Gemini, it looks structured. It has order to it. The other one kind of does, kind of doesn't, but this is kind of where it was hard for me to show a lot of differences. So I have a few pictures that we can just go through and talk about. And I wanted you to talk about predictable crystal growth in meteorites. Does that make sense?
Yeah, certainly. So the meteorite you're showing on the right, which is Gemini, has a spindly plessite structure to it. And so you can see that the crystal growths within the camosite are all kind of randomly oriented. It's not an octahedral structure per se. But if you look at the slag on the left, you get a lot of orientation of those crystals. So you can kind of see the little hump on the upper left-hand side of that piece is like a nucleation point, and they're actually radially aligned, growing out of that kind of origin point. And obviously, there were other origin points. There's some crystals that are sticking more like out towards the viewer. So there's multiple origins there, but they have a structural growth that's like a spherical nucleated site growth. And you won't see that in the meteorites because it's not individual grains from a nucleation point spreading out in the metals like you would get in like a radial pyroxene, for instance,
Yep.
on a silicate chondrule. You're going to get that random pattern in anything that's got placitic structure to it. And so that's kind of one of the bigger giveaways.
Thank you, man. And just to give everyone scale of what we're looking at, you'll see the picture on the right, the slag. Those lines in the background, that's someone's palm print. So that's fingerprint of someone's palm. And these are at the same scale. This is what you were just talking about. It looks like nucleation points in the center and growth going out 2 sides. That's not a shape of a meteorite structure.
Yeah, exactly.
I'm not even sure what kind of industrial waste this is, but it grew out in crystals and it looks like this. I mean, so you are going to get to see some fine details in your slag, in your industrial waste, just again, depending on all of the plethora of variables that we mentioned earlier. But when you see structure, that's logical, that's aligned. It's super easy once you become accustomed to holding, looking at, touching meteorites to know this is an organized structure. This belongs. This is a meteorite. The other one had like it didn't have the shape of meteorite structure, the crystal growth. And these are things you see when you look up close, like maybe even under microscopes. Again, another example of Ammoniana lusta here. And this one shows really, really good pattern as well. You'll see that it's all lined up. You're seeing cross hashes. You're getting the pyramid shape. There are, I think Mike's going to talk about octahedrons and stuff like that later. But depending on how, because there is a predictable crystal growth on the inside of an iron meteorite, if you cut it, you can predict exactly, if you know the angle, what that structure will look like from the inside. So that's what we're looking at here is the crystal growth metal plates.
The Altai and the Munialustia are both octahedrites, so that's a double pyramid structure. So imagine a pyramid upright and a pyramid upside down to make your 8-faced figure. And so what you're seeing in this still, right, is you're cutting into one of those faces. So that's why you're getting a triangle, right? You're following that triangular plane. Now, if you were to cut through the top, you would get a square pattern, right? Because you're cutting all 4 of those faces evenly. And then as you change your angle of your cut, depending on how you slice that meteorite, you're going to get elongation of those triangles into a more pointed type triangular face because you're not cutting all of the faces evenly. But yeah, the octahedrites are always going to have that same triangular or squared pattern depending on which angle they were cut at. And again, you won't get very much randomness. You'll get other crystals of things growing in there, screebersite, cohenite, all those other things that'll disrupt the pattern. But the bulk of the pattern will be those triangles or those squares.
Well done. And I did want to include this for our Star Wars fans out there. I couldn't resist. Uh, just so you guys know, because we were just talking about cutting, looking at the inside of potential meteorite or slag. I just wanted to be very direct and put it out there. Everything we talked about earlier about you don't know what's in there. Do you really want to grind it and breathe it? No. The answer is no. Let's use a little bit of common sense. We actually had some samples that were delivered to us as potential meteorites, and we literally got sick. Sue and I both had breathing issues, and we had to wash our hands and bag them up and get them into a different room. It's industrial waste. You know, it has all these heavy metals. It could have arsenic, zinc, copper, all kinds of bad things in there. You definitely don't want to be grinding on it without a respirator. You definitely don't want to be inhaling small bits of it. Mike, what else am I forgetting, man?
Yeah, and some of that stuff actually will absorb through your skin, right? So, like you said, wear PPE, proper protective equipment. Wear gloves when you're handling it, if possible. Wash your hands afterwards. Just be considerate of the fact that, yeah, you have no idea what's actually in there. It's not, most of it's not good for you to begin with.
Yeah, it's waste for a reason. They're giving it away almost for a reason. I thought this was a really good picture just to take out. I don't expect you guys. There's not a test. You don't have to. But it's from the a civil engineering book. So civil engineers do everything that we were talking about today, with roads, boats, shorelines, infrastructure, landscaping, buildings, construction, deconstruction as well. In their own books, they have their own health and safety biohazard warning segments just for slag, just for industrial waste, just to be very aware that it's not a piece of limestone off the ground. It came from a factory. It's waste. They kept the good stuff and threw away this, and now you're going to be breathing it and putting it in your mouth. No, let's not do that. Yeah, I also wanted to say, beware, because people are selling slag as meteorites, and we showed some beautiful slag earlier, but these are not beautiful slags, okay? And they're not calling them slags. So when you're seeing something for sale, and it's a really crazy high price or crazy low price. The description doesn't match, or it's a vague description at best. If they don't show you any internal features, any internal slice or side or anything like that, if they don't accept returns, these are all huge red flags that you're probably going to be stuck with that piece of industrial waste if you bought it from them. So just word to the wise, be careful, be wary out there, and don't spend $60,000 on this lunar slag meteorite rock, okay? No matter how beautiful you think that is industrial waste. A 77, even if it was 77 grams of real lunar, Mike, it's only like, $30, $40 a gram for lunar. You're looking at, it's crazy. Here's another one. I don't know what type of slag. My goal was to learn enough so I could identify all these slags. I didn't pass my own test, but that's definitely a $2,000 hunk of garbage that you don't want. Again, look at the vague description. Large meteorite rock. No weight, no type, no nothing. And they want $2,000 for it. You know what I mean? Yeah. So here's another one. $12,000, which works out to $115 per gram, and we have no idea what it is. It's just a meteorite. That's all you get. But of all the pictures we showed you in the last hour, however long we've been doing this, look at that. If you can't identify that as slag right now, please go back to the beginning of the video and try again, because that is a perfect example of slag, and it could be yours for $12,000. Here's another one. 55,000. Yeah, they call it a meteorite, possibly. Yeah, it's ridiculous. It's 10 kilos, so big sizable one. But definitely, we're seeing 100% of slag and industrial waste features in this one as well. Again, they're calling it a meteorite rock. It may appear to be a mesosiderite-ish, but it's too pitty. The silicates are not flat enough against the metal. The dispersion isn't right. It just doesn't look right, and we don't even know how much it weighs. It could weigh 5 pounds, could weigh 5 grams. We have no idea. So with that being said, I will say if you're gonna buy a meteorite and you're gonna spend money on what we think is a luxury item, you might as well go to someone reputable who's known and buy it from them. That way you don't feel like a jerk when you show it off to someone and then you get called out for having a piece of slag and saying, look at my piece of the moon. I guarantee you anything and everything you buy from myself or anyone who's an IMCA member is going to be a legitimate meteorite. So I would love for you to take a look at our eBay shop and support what we do here. In addition to using only reputable sources for your meteorites, we're really glad that you are using our channel, our Knowledge Bolide crew, for your ingestion of meteorite and scientific materials. This was a labor of love. This took a lot of work. We probably have about 50 plus man hours into this already, and I'm going to have another dozen editing and stuff. But Sue really did a great job putting all these slides together. Mike did this presentation 3 times now, so thank you very much for your patience. As always, you're one of the most valuable crew members we have, so thank you very much, sir. I also want to extend a good thank you to our Patreon and our YouTube supporters, our paid supporters. You can subscribe to our channel, but you can also join as a member and get extra videos and features. And realistically, when you do something like that and you support us on Patreon or on YouTube, you help videos like this get made, because I am not an industrial waste expert, but I became one for this. Sue became one for this. We took a lot of time putting this together. A lot of time was spent educating this, putting it together so we can be out there for the entire internet to consume and everyone makes smart decisions. So just know that if you're one of our paid backers, you're responsible for this video, and we thank you from the bottom of our hearts, because it really does mean a lot to us that we can invest the amount of time we needed to get this video up to the level that we think you need. So thank you guys. Thank you very much for your support. Well, now that I've thanked everyone, I got to ask for some help. No, this is the first episode. There's a lot of information, a lot of conversation. We've had our crew, our Knowledge Bolide crew, all of them on mute for the last hour and a half. They're dying to get off of mute and start talking about slag and showing their examples. So it's going to take me 2 weeks to get it edited, get it up on YouTube, but we're going to give you guys about a month after it's up for you to get in contact with us. All of our contact information is in the description of the video. If you have any of these examples that you want to be featured on our show, we showed a bunch of examples today of garbage slag, a bunch of beautiful slag, art slag, stuff that's in museums and stuff that's in art exhibits. So we're not knocking you for what you bring. We want as many examples of as many different things as we can. Let's crowd surf this together and see if we can't get a really good collection of slag, because if you go online, there's only one web page that really has a good selection of slag, and we use and abuse Randy Koretev's webpage for this production. So a final thank you to Randy Korotev. I wanted to thank everyone. I want to thank you for your patience. I don't know how long this video is going to be when we're done editing it, but we were not going to do this half-assed. Mike, once again, from the bottom of my heart, thank you very much, sir. You did a great job, and I really appreciate all the time you put into this. Look at this crew. What a good-looking group of people. Holy crap. All right, guys, let's wave to the camera. Thanks a lot, everyone. I appreciate everyone's help. Have a great one.